A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we'll be talking about bipolar junction transistor as an amplifier. This lecture is a part of lecture series from the course of Introductory Electronics having the course code of PHY 201. In today's lecture, our basic objective is to understand the use of BJT as an amplifier. How it can amplify the input signal. And the other objective from this lecture is to understand the usage of BJT as a switch. And finally, in the end of the lecture, we will also try to identify the BJT. The BJT as an amplifier. Amplification, everybody knows that amplification is actually the increase in the input signal. So in the case of amplification, a relatively small AC voltage can be had by placing the AC signal source in the base current, and this because we already understood in the previous lectures that small changes in the base current causes large changes in the collector current circuit. So that is why we can use BJT as a sort of amplifier. Here look in this signal, the circuit, it is actually the circuit with input AC voltage, that is actually called as V in, and DC bias voltage is superimposed. So what happened, this is actually the input voltage, and you see the intensity of it is small, and the output is like this, and this is in the waveform. When you see this the signal is amplified. In this particular case, the AC emitter current is represented by I small I in the subscript of I small e, that is almost equal to the collector current, and that is equal to Vp divided by Re. And similarly, the AC collector current is voltage is equal to Vc is equal to Ic Rc, and is here we can use, so we can just replace Ic by IE. So what happened from this, we can find out the ratio of Vc to Vb in the AC voltage gain, that is AV is equal to Vc divided by Vb. And when we put the value of IE Rc for Vc, so what we can get the amplification terms, and that is AV is equal to Vc divided by Vb, and that is almost equal to this value. So in this particular case, the term IE cancel, and what we can get is AV is almost equal to Rc divided by Ra. So this is the use of BJT's amplifier. So we are coming towards the usage of BJT as a switch. By switch we mean that we can use sometime the BJT in cutoff mode and sometime in the saturation mode. We already understood the different modes of the BJT from last lecture. We understood that there are two different modes, that is actually the extremities. One is the cutoff mode. In this particular case, there is no collector current in the cutoff mode, and the other is the saturation mode, in which we have the maximum collector current. So if we use the BJT in the cutoff mode, so that is the switch off mode and the signal is off. Keep in mind, here is the circuit diagram for the cutoff mode, and in this particular case the signal is not passing through the BJT, and this BJT is exactly working like open circuit, and circuit is open, and current cannot pass through that. In the other extreme case, we have the saturation mode, and in the saturation mode, this is the circuit diagram for the saturation mode. So what happen in this case, maximum current passes through the BJT, and this is actually, this circuit is working like switch on circuit. Now coming toward the condition of cutoff and saturation mode. So if we consider a transistor, when it is in cutoff region, then the base-emitter junction is not forward biased in that particular case, and all of the current is zero. And in this particular case, the VCE, the voltage across the collector emitter, should be equal to VCC. So this is actually the specific condition for that. and in this base-emitter junction is forward, right? When the base-emitter junction is forward, right, there is enough base current to produce a maximum collector current. The transistor is saturated. So this is actually the saturation mode. I mean the in saturation mode, base-emitter junction is forward bias and there is maximum current passing through that. So the formula for the saturation current is like that IC is equal to VCC minus VCE divided by RC. So what we can get the base current, minimum base current for that. For the saturation current, it should be equal to IC, the saturation current, divided by beta DC. How we can operate the transistor? This is actually a review of the previous lectures. I mean how we can move through the transistor operations. I mean this is the simple diagram in which the majority carrier and minority carriers are represented. Here we are looking, this is actually the emitter region, this is the collector region, and this is the base region. If we look toward this, the emitter region is this is forward bias. This emitter base junction is forward bias. This is connected to the source, and this is actually the depletion region, the very small depletion region over here, and the depletion region over here is a big, comparatively big. So what happened when the emitter base junction is forward bias and the collector base junction, this is actually the collector base junction, is reverse bias, then due to this high voltage, some of the electron can penetrate or pass through this tunnel through this N, the base region. So what happened? We have maximum collector current that is received over here. Some of the electrons or some of the carrier meet with the electron in the base region, and as a result they are contributing to the base current. So that will lead to the base current that is represented by IB. Keep in mind the magnitude of collector current is around 19 to 95%, while the magnitude of the base current is around 1 to 5%. So it depends upon the doping level and the configuration of the BJT. But anyhow, the magnitude of collector current is very much greater than the base current, and the base current is only used to control the collector current. So the different currents in the BJT could be represented here. We have basically three currents that are used in BJT. One is the emitter current, collector current, and the base current. And if we look toward the magnitude of this current, then the magnitude of emitter current should be equal to the sum of the base current and the collector current. So the collector current is comprised of two currents, that is actually the combination of majority carrier and minority carriers. So IC should be equal to IC majority plus IC or minority carriers. So this is actually, if you look toward this arrow bar here, it is very clear from this arrow bar that this is a really big arrow. It shows that the maximum current flow through this region, and the magnitude of the arrow, I mean the even from the representation, is very small. So it seems to be that small current is flowing through the base region. We have different configuration for the BJT, that is the Common-Emitter Configuration. This is a simple common base configuration of the BJT, and that how we can use this BJT, that is a PNP transistor, and this is NPN transistors. And in this case, in both the cases, we have a common base configuration. So what happens? The current is flowing like this. This is the conventional direction of current. A maximum current flow through this region, and a small current flow in this region. This is actually contribute to the base current. This is the direction of a collector current. Here in case of NPN, the direction of the current is opposite to that. So it's like that this is the collector current actually, because its electronic current is a type of NPN transistor, so that is why its direction is opposite to the PNP transistor. And this is the base current, is represented by a small arrow. So this is actually in this particular case the base is common to both input, that is emitter base, and output, that is collector base of the transistors. We have common base amplifier. I mean, how we can use the common base amplifier, I mean, and amplify the input signal. This is actually the input signal, and this curve shows the relationship between the input of current, that is IE, to the input voltage for the three output voltage, that is VCP. So here we have the curve that is drawn between the voltage and the current. The current is measured in milliampere, while the voltage, that is actually measured in V. So we have this. We can also use the common base amplifier. In case of common base amplification would happen, we have some characteristic for that, and this is the output characteristics of common base amplifiers. The curve is drawn between the collector current and the collector to base voltage, and this is the particular cutoff region, and this is the saturation region where we have maximum current that is passing through that, and this is the value of the collector current, and this is the active region where we have the different values for that. In this case, the collector current is equal to 0, where in this case the collector current comes from 1 milliampere, 2, 3, 4, 5 and 6 up to 7 milliampere. I mean, we have the curves for that. And we have operating regions for the transistors. There are different operating regions for the transistors. We already discussed. This is also called as modes of the transistors. We have the active operating region of the transistor. In this particular case, we can use the transistor as an amplifier, and it can amplify the input signal. The signal that is given to it is the magnitude of the signal that is given to it is smaller than the magnitude that it is giving as an output, so it means that it is amplifying the input signal. We have the other mode, the other operating region of the same transistors, that is actually called as a cutoff mode or the cutoff operating regions. In this particular case, the amplifier is basically off. The amplifier is basically there is voltage but little current is passing through that, and we have the saturation operating region of the same transistors. In this saturation transistor operating region, what happens? The amplifier is full on, and the current is there is current but little voltage is there, and that current is produced through this particular region. So this is actually the operating regions of the simple transistors. We have the some factors that is actually describing the ratio between different currents, and that also describe the magnitude of current between the different regions. These are actually in some cases basically we will have some problem regarding this, and in which some values will be given to us, and we need to calculate the unknown values. So therefore these relations are very much important, and from this relation we can find out the unknown values. One of the relation is the alpha relation, and that actually describes the ratio between the collector and emitter current. So the alpha DC is basically equal to I C divided by IE. Keep in mind both C and E are in the subscript, so this is IC divided by IE. If we have an ideal configuration, then the collector and emitter current should be equal to each other, and the base current should be equal to 0. But this is really is a type of rare and is not possible almost. But anyhow, this is actually type of ideal configuration, and in this ideal configuration, the collector current should be equal to the emitter current. So when both of them are equal to each other, then they will cancel the effect of each other, and the value of alpha DC should be equal to 1. But in reality, if we look in reality, the value of alpha DC, it's fluctuate between the 0.9 0.9 to 0.998. This means that the magnitude of alpha and the emitter current should always be greater than the collector current, and that is actually the reason that some of the current pass through the base, and so that is why the value of alpha should always be less than 1. So normally normal operation it's varies, it is fluctuating in the region of 0.9 to 0.998. Alpha in case of AC mode it will be a bit different, and that is actually describe the change in the collector mode. So in AC mode it will be alpha AC should be equal to del I C divided by del I into subscript in the subscript this is mentioned. We can use the transistor amplification in which we can increase the input signal. Here is the circuit diagram for the transistor amplifications, and in this particular case we have a external potential difference, that is a type of AC voltage is provided, and the magnitude of AC voltage is there is this the magnitude of AC voltage is 200 millivolt, and this is the emitter current, and we have collector current out of that, and the value of the resistors is given here. So we have current and voltage, in magnitude is specified here, and we need to know the current and voltage gain to the difference region. So what is the effect of that? So this is the input voltage. So we have the current and voltage that is mentioned here. The magnitude is clarified. We have the emitter current, this magnitude is 10 milliampere, and collector emitter current is almost equal to each other. So this is the voltage gain, and this is actually the ratio what we had developed in the previous slides. So from this we have the amplifications like voltage gain that is equal to 250. So this means we can use the same transistor as amplifier. So this is a type of a problem solution on the transistor amplification. In the same way we have many problems that is possible, and that could be used to to amplify the input signal, or even we need to calculate the magnitude of amplification. So in this particular case the magnitude of voltage gain is equal to 250. We have the common-emitter configuration for that, and this common-emitter configuration of the type of BJT. In the common-emitter configuration, the emitter is common to both input that is a base-emitter, and the output that is collector emitter. So the input is in the base on the base, and the output is in the collector. So this is the simple configuration of the common-emitter configuration. So here we have the current is represented over here. This is a type of NPN transistor. So this is actually the direction of current in this particular case, and this is the common-emitter configuration. We can also draw the characteristic curve for the common-emitter configuration, where we have the active region. This is the active region. We have the cutoff region over here, and we have a saturation region over here. This vertical axis represent the collector current, that is represented by milliampere, and this is the voltage, that is CE. So that is represented. So this is the collector characteristic, and from the base characteristic we can find out the different value of ECE, and that could represent the curves between the base current. You should keep in mind the magnitude of base current is always represented in micro ampere, because its magnitude is very small, and that's represented over here. So we have common-emitter amplifier currents. That's ideal current is the that the emitter current should be the sum of base current and the collector current, and this is the alpha that is could be multiplied with that. If we do a cross multiplication, actually alpha is equal to IC divided by IE. So after cross multiplication we can get that. So if we put the value of IC over here, so what happened, we can simplify this equation like this. Keep in mind we have some sort of minority collector current that is over here, so that could be represented. So if we put some value of 0 microampere when the base current, we can get the value of IC in this particular case. We can also get the value of beta. Beta represent the amplification factor of a transistor, and is also represented as a HFE in some terms, that is actually called in particular case. So beta this is actually the ratio between collector and base current, and in AC mode it is actually the change in current between the collector and base currents. So we have the characteristic of beta, and that is actually drawn between the collector current and the VC voltage. So from that we can solve the value of beta and the amplification as well. So beta this is this is actually the simple relationship between alpha and beta. Alpha is equal to beta divided by beta plus 1, and the same if we can solve for alpha. So for beta, so beta should be equal to alpha divided by alpha minus 1. And there is also relationship between different currents. The collector current is equal to the base current multiplied by beta, and similarly the emitter current is equal to beta plus 1 into the base current. So we have common collector configuration. In this particular case, the input is in the base and the output is in the emitter. This is actually called as the common collector configuration. This is the sample diagram for the common collector configuration. This is PNP and this is NPN transistor for the common collector configurations. We have the characteristic curve for the common collector configuration as well, where different currents are presented here, and the curves are drawn between the collector current and the voltage, the collector to emitter voltage. So these characteristics are similar to those of the common emitter configurations, except there are some changes. That is, the vertical axis is IE in that particular case, and in this case is IC. We have the operating region of the this particular case. This is the operating region. We have the the value over here. We have the cutoff region over here, and the saturation, very small saturation region is represented over here in this particular case. We can also identify the terminal of the transistor from a simple case. Here we have some of the example. We have the different sort of transistors. This is actually the types of transistor what we have, and how we can identify the collector, emitter and base from each other. So in some cases very clearly written that this is C, this is B, this is E. C represent collector, B represent base, and E represent the emitter. So from that we can easily understand that which port is represent which thing. So this is something about the transistors amplifications and its understanding and characteristics. Thank you very much.